In this video, you will learn to compute some basic measures of statistical series, in particular the mean, the variance, and the standard deviation of a statistical series. Not only will you learn to apply formulas of these measures, but more importantly, you will fully understand the intuition behind all these formulas. Let's start with the mean of a statistical series. A statistical series is simply put a list of numbers, like the following list. Here, for example, let's say that this series represents the grade of 10 students on a math quiz under the variable x. X here will represent the student's grade. So x sub 1 is the first student's grade, x sub 2 is the second student's grade, x3 the third, and so on, up to x10, which represents the 10th student's grade. To better appreciate a list of numbers, you may compute what we call the mean of said list. The notation of the mean of x is an x with a line on top, and this measure answers the following question. What if we redistributed all the marks students got so that everyone has the same grade? What would be that grade? For instance, those with a high mark will have some marks taken away from them and given to those with lower marks up to a balance where everyone has the exact same grade. So the formula for the mean seems somewhat complicated, but it is not at all. It's 1 over n, where n is the number of elements in our list, or the size of our list, here 10. Then we have the summation symbol, often read sigma, and it tells us to add all the values of our list. So to find the mean of a list, in the denominator you have the size of the list, here 10 students, and in the numerator, you have all the values of x and add them all up in the numerator. We can replace x1, x2, and on by their respective values in the list, add all these numbers together, and you get 120 in the numerator, which divided by 10 gives us a value of the mean equal to 12. So on average, students got a mark of 12 out of 20 on their math quiz. So to summarize, it's quite simple with the mean. You add up all the values of your list and divide by the size of the list to get the mean. The second important measure of a statistical series is the variance. The mean is a good measure, but it tells you little about how the data points of a list are distributed. And so the variance is a measure that's as important as the mean. For example, here are two additional lists that have also a mean of 12. However, these lists are very different. Look at the list in the middle. The mean is equal to 12, but no student has a mark close to 12. The students are either way below the mean or the students are way above the mean. In the bottom list, however, all students' marks are really close to the mean. Every student's mark is close to 12, so close to the mean. And the variance is a measure that allows us to compare these two lists. The middle list has a high variance because the values in the list are generally far away from the mean, but the list in the bottom has a low variance since the values of the list are generally close to the mean. And so to come up with a formula reflecting this concept of variance, we have to ask a simple but fundamental question. And the question is, what is the difference between the values in my list and the mean? For example, the students that got 7 out of 20 is 5 marks below the mean of 12, since 7 minus 12 equals minus 5. The students that got 8 out of 20 is 4 points below the mean. And so we can compute all these gaps between values of the list and the mean by doing the difference between each value and the mean. These gaps are called deviations from the mean. It reflects how much each value deviates from the mean value. The larger these deviations from the mean, the larger the variance will be, and the smaller the deviations, the smaller the variance. And so a natural way to define the variance is by taking the mean of all these deviations. By taking the mean of the deviations, you will know on average how far away your data points are from the mean. So it would be the same formula as the mean, except we would sum up the deviations from the mean instead of the data points themselves. However, this formula has a serious problem. The deviation from the mean can be positive or negative, and by design, the positive and negative deviations will cancel out when you sum them up, and our variance will be equal to 0 for any statistical series with such a broken formula. And the problem here is that we are not interested in the sign of the deviation. A deviation from the mean of +4 or a deviation of -4 should have the exact same effect on the variance. And so to resolve this issue, we will consider the squares of the deviation instead of the deviations themselves. Why? Well, think about it. The square of a number is always positive, so it doesn't matter whether the deviations from the mean is positive or negative. The effect on the variance will be positive no matter what with such a formula. Another option would have been to consider the absolute value of the deviations, which would also resolve this issue. However, the absolute value function is generally harder to work with than the square function, and so conventionally, the variance is defined as a function of the squares of the deviations. So here's the baseline definition of the variance. It's the mean of the squares of all the deviations from the mean. So in our example, to compute the variance, in the denominator you have the total size of your list, so 10 students here, and in the numerator we have all the deviations from the mean. We square each deviation, and then we sum up all those squares. Here, if you sum up the numerator, you get 98, and 98 divided by 10 gives us 9.8 as the result for the variance of this list. If you find the variance formula too complicated, there is a simpler yet equivalent formula that you can use. We can prove, and we may do it in another video, that the variance is equivalent to the mean of the squares minus the square of the mean. Let me repeat. Variance is equal to the mean of the squares minus the square of the mean. We already know the mean of x, so all that's left to do here is to find the mean of the squares and then apply the formula. To find the mean of the squares, so x squared with a line on top, in the denominator we have the size of the list, so 10 students here, and in the numerator we take all the values in our list, we square those values, and then we sum up all those squares. Here we get 1538 in our numerator, which divided by 10 gives the mean of the squares equal to 153.8. We are now ready to apply the variance formula. We first take the mean of the squares that we just computed, so here 153.8, and subtract the mean itself squared. So the mean of this list is 12, so here we subtract 12 squared from 153.8. We get 153.8 minus 144, which equals 9.8, so the same value we got when we applied the first formula. Now that we understand what variance is, we are ready to define the standard deviation of a list. The standard deviation is usually represented by the Greek letter sigma, and the standard deviation is intimately related to the variance. It's indeed the square root of the variance. Remember that when we defined the variance, we used the square of the deviations in our formula, not the deviations themselves. And so, to have a measure that is directly related to the deviations themselves and not their squares, we have to take the square root of the variance to find the standard deviation of our list. In our initial example, we had found a variance of 9.8, and so the standard deviation of that list is the square root of 9.8, which is equal to 3.13. And what this measure tells us is that on average, students are 3.13 points away from the mean. When we pick a random student from this class, we expect the student's mark to be 3.13 points above or below the mean. Unfortunately, the standard deviation measure has one pretty significant limitation. In our example, the student's mark were out of 20 points. But what if the grades were converted to be out of 10? All the grades would be reduced by half, and so would the standard deviation. Similarly, if we doubled the values of our data points, we would double the variance. In other words, the standard deviation is very sensitive to the unit of measure. If you have a list measuring time in hours, for example, and the exact same list measuring time in minutes, the latter would have a standard deviation 60 times higher since there is 60 minutes in an hour. A list measuring distance would have a completely different variance depending on the unit of measure chosen. And so to resolve this issue, we want to create another measure of variation that is unit independent. Let's call it the coefficient of variation and denote it by C sub v. And the most logical formula would be taking the standard deviation and dividing it by the mean. That way, you know the deviation from the mean as a fraction of the mean itself. The coefficient of variation will therefore be a value between 0 and 1, and it will be the same value no matter the units you choose for your list. In this example, the coefficient of variation is equal to 3.13 over the mean of 12, which is 0.26. So we can say that on average, our data points are 26% away from the mean. So this concludes our video for today. I hope you learned something new. And if you did, please drop a like on this video to help me get started on YouTube. And also hit the subscribe button. And until then, be excellent.